Hello, everybody. Uh, I'm here to present my subdiscipline presentation here. Just want to say, Nick, that this is difficult. I'm not used to not talking to an audience, and I'm not used to seeing myself talk and then stopping it and listening to myself talk. Anyway, but I'm going to give it a shot for the umpteenth time. And as I'm going through this, I'm going to give you a few background slides just to let you know kind of what I'm working on. And I'm looking at marsh mangrove elevations, specifically the influence of elevation on the establishment and growth of Abyssinia germinans, or black mangrove, which is a tropical to subtropical coastal plant mangrove. And I also want to know how this establishment of black mangroves is going to affect the ambient marsh. So what I'm looking at is as the range of black mangroves expand with climate change, and climate change being less frequent freezes, how is that going to affect the marsh specifically? How is it going to affect the marsh's ability to keep up with rising sea level? So again, some more background. And this comes from Oslin et al. 2017, showing the expansion and contraction of mangroves in South Louisiana, specifically Port Fourchon. And this is a graphic showing from 1978 to 2011. You have 1978, a contraction between 1978 and 1993, and expansion from 1993 all the way to 2011. And you show this expansion and contraction. In 1989, you had this really hard freeze that really knocked back mangroves in South Louisiana from probably around 400 hectares to as low as 41 hectares. And this expansion and contraction is shown here in this modeled and photo interpreted graphic. And what you have is this is the 1978 photo interpreted graphic to 1993 after that really hard freeze, 2000 and then 2011. And as these freezes become less frequent, mangroves are going to expand. And that brings me to my first subdiscipline, which is climate change science. Mann et al., 1999, Northern Hemisphere temperatures during the past millennium, inferences, uncertainties, and limitations. We all should know this particular paper because this is what is famously referred to as the hockey stick graph. And this graph shows temperature anomalies from in the past millennium, and when actual data started being recorded, and around the turn of, or around the advent of the industrial era, and the pumping of CO2 into the atmosphere from burning of fossil fuels, our temperature anomalies have started going, the temperature has started rising up and up and up. And again, this is the curve that kind of started all of the man-made climate change scenario in the early 2000s. Every school kid sees this, should see this and understand this graph up to this point. And the change in temperature is largely driven by the change in CO2. How we've been pumping out CO2. This graph here on the left is actually from Mann et al. 1999, and it shows as we pump out that CO2, our temperatures are rising with that, kind of paired with that graph in that paper. And we use this to this day to look at scenarios, warming scenarios, and sea level rise scenarios. This is always tied to an emission, a CO2 emissions. If we cut back CO2, which we're doing now. Yeah, cut back CO2, and if we keep on business as usual, what's going to happen with temperature, sea level rise? We look at that to this day. So as the temperature warms, my mangroves will be able to expand northward. And what my next subdiscipline kind of what's keeping the mangroves from expanding northward, and that's plant physiology, specifically freeze tolerance in black mangroves. And I've used this paper several times, and I've queried several black mangrove scientists, and this paper is the paper that keeps coming up in freeze tolerance and in the physiology of black mangroves. A little bit of background on this one. This is the northern range, or the North American range of black mangroves, and that North America range runs from roughly on the Atlantic coast from Jacksonville, and then in the Gulf Coast, the northernmost mangroves are typically here in Texas Point, right here at the Texas-Louisiana border. There have been a few occasionally on the barrier islands of Mississippi, but this is the northernmost range, and they're limited to this northernmost range because when temperatures drop below, according to Stewart et al., 2007, the role of freezing in setting the latitudinal limits of mangrove forest, that at a general temperature of -5 degrees C, you have a xylem embolism that kills the plant. Mangroves don't go dormant during the winter; they're constantly growing. So when a freeze occurs in excess of -5 degrees C, it typically kills the plant. And this has led to research such as this, Osland et al. 2018. And this has kind of better defined that range. And the threshold range of minimum temperature seems to be -7 degrees C. So anywhere where the lowest temperature doesn't get below -7 degrees C, you could, in theory, have mangroves. And with refugia and maybe some time to grow some bigger mangroves, you might be able to get below that threshold some. But just to drive that point home, this is from the National Climate Assessment, 2014 National Climate Assessment. And you see from 1971 to 2000, the number of freeze days below 32, the 0 degrees C. And you see it matches really well with the current range for black mangroves. And then you have the projected freeze days from 2041 to 2070. And what you see here is a northern shift of the lessening of the number of freeze days. And this basically means that by 2100, you could have black mangroves establishing throughout coastal Georgia up into South Carolina. I've even seen a model that shows them all the way up into North Carolina in 2021. And then this brings me to my third discipline my third subdiscipline, marsh hydrology and geomorphology. And for this, I'm using Morris et al. 2002, Response of Coastal Wetlands to Rising Sea Level. And this paper is, I've used this paper a lot, and this paper is cited a lot because this is where what is called the marsh equilibrium model comes from. And what the marsh equilibrium model says is that at a certain rate of productivity and sedimentation, the marsh platform is able to keep up with sea level rise, with a certain rate of sea level rise. This basically D, what's represented at platform depth here, which is the marsh platform below mean high tide. You see as above ground production increases, you can have the depth of mean high tide higher. And this represents a low marsh, which is a really productive marsh, and high marsh here. And at this point, this is a stable marsh. It's able to keep up with sea level rise. And if it gets any deeper, no amount of production will be able to keep that marsh platform stable. And it's emphasized here through many years of fertilized treatments and control treatments. You see the fertilized treatments are basically accreting at 0.71 centimeters per year, and the control treatments at half a centimeter per year. It's able to keep up with sea level rise. Now, you throw in sedimentation into this mix, and then you have a really good way for the marsh platform to keep up with sea level rise. Here you had to see two different, a highly productive marsh, this is a productive marsh with high sediment load, and a low sediment load. And what you see here is that with high sediment and high production, optimal sea level rise rate is about 1.25 centimeters per year, which is actually incredible. That's 1.25 centimeters of sea level rise per year, relative sea level rise relative to the area. This just happens to be North Carolina, in a Spartina alterniflora marsh. And in a marsh that doesn't get as much sediment, the maximum productivity, or the optimal sea level rise rate for this particular marsh, where it can stay stable, is about 0.63 centimeters per year. And Dr. Morse, with this marsh equilibrium model, has demonstrated through measurements and modeling, has shown that these marshes, these Spartina alterniflora marshes in North Carolina, have been able to keep up with sea level rise. And that is what I want to know with my data, is how as the climate warms and the freeze events become less frequent, is how is this black mangrove going to affect the marsh platform? Is it going to be able to keep up with sea level rise like the Spartina marsh here, which you see here, or as the mangroves take over and replace the Spartina, is that platform going to be able to keep up with sea level rise? So that's what I want to know. That's kind of where all my subdisciplines come from. So I want to thank y'all for watching, and just let y'all know that this is a really difficult thing to do, because there's nobody there, and turns out I sound like a real hick, and nobody flipping ever tells me. Anyway, I miss you guys. I miss our discussions. I'll talk to you later.